Hello everyone, welcome back to my YouTube channel Unfog with Dr. ATAHAR PARVEEN. In this video lecture, I shall discuss molecular orbital theory from HSTR and KREIS chemistry syllabus. The syllabus includes salient features of molecular orbital theory or M.O.T. and its formation by LCAO method. Here LCAO means linear combination of atomic orbitals. This molecular orbital theory, it is based on quantum chemistry. It treats the atomic orbitals based on quantum chemistry, or you say quantum mechanics or quantum physics. So, before we discuss molecular orbital theory, we need to know few terms based on this quantum chemistry. For example, terms like wave function. What is wave function? We know that from dual nature of light, that light can behave as a wave as well as particle, right? If you have attended my GPSTR classes, you will know all these concepts. In the same manner, a particle can behave like a particle as well as a wave. Now, this wave function, it is a variable quantity that will describe this wave characteristic mathematically. This wave characteristic of this particle, or in simple words we can say that a wave function, it describes the position and state of electron. We denote this wave function by a Greek symbol psi, and if I take the mod of this psi, means if I write mod for this psi and then I take the square of this psi or this wave function, then I get what we call as probability density of electrons. So this mod psi square will give you the most probable place where an electron can be found. Now what is the most probable place where an electron can be found? It is orbital, right? That place we call it as orbital. So let's talk about what is orbital. First of all, what is a orbit? Orbit means it is one well-defined circular path around the nucleus. If this is a nucleus, you have a well-defined circular path around this nucleus where electrons revolve. So this circular path, we call it as an orbit on which the electron is moving or revolving around the nucleus. But what are atomic orbitals? These atomic orbitals, they are the 3D space. This is just a plane space we are talking, right? This is just a plane space. Atomic orbitals, they are the 3D space around the nucleus where probability of finding an electron is maximum. Means my mod psi square is maximum. You can find or you can determine the orbitals using this mod psi square. We have shapes of atomic orbitals, right? So what are the shapes of atomic orbitals? There are 4 shapes of atomic orbitals. They are s orbital, p orbital, d orbital and f orbital with different shapes. S orbital, it will have sphere shape. P orbital, it will have a dumbbell shape. D orbital, it will have a double dumbbell. Double dumbbell means, see, this is one dumbbell and this is another dumbbell. So it will have a double dumbbell shape. And F orbital will have a shape like this. Means dumbbells inside a cube. Okay. With that touching those corners, you can say. So how many dumbbells will be there here? 1, 2, 3. 3 pairs of dumbbells. Means you can say that triple dumbbells are there in F orbital. Anyway, we don't bother about F orbital much. Even d orbital we will not talk much. We are interested in knowing more about s orbital and p orbital. Now, molecular orbitals, how they are formed? They are formed by combining these atomic orbitals. Actually, the concept of orbitals, it was explained by Heisenberg's uncertainty principle. We'll come to that later. We'll talk more on this atomic orbitals. Now we were talking about the shapes, right? Now, when we are talking about this probability density of electrons, we should know where the electron is found, isn't it? We should know where the electron is possibly found around the nucleus. There are few places where electron is surely we can find it, but there are few places where we absolutely don't find electrons. For example, if I take the S and P orbitals, this is the shape, right? For S orbital, we have a sphere shape. In S orbital, electrons can be found anywhere. This is the sphere shape. But then in P orbital, you can see that the P orbital is dumbbell shape, right? So if one part, if it is positive, means the other part will be the negative. Now where these two shapes meet, no, this point is known as node, N-O-D-E, node. This node, this is a point where electron will never be found. Electron will surely not be located there in this node. Okay, no electron. This is the place where we don't find electron. That means that if you have more nodes in that orbital, energy will also be higher. Okay. Now here I can clearly show you this Px, Py and Pz orbitals. Px orbital means it is along x direction. Py orbital means it is along y direction. And Pz orbital means it is along z direction. We are bothered about the directions because we will talk about the overlapping of the orbitals here, right? So that's the reason I am showing you this picture. Now let's come to the concept of the Heisenberg's uncertainty principle. I told you that the concept of orbitals was explained by the Heisenberg's uncertainty principle, right? So actually, see, we were talking about this Heisenberg's uncertainty principle during our GPSTR classes also. I have taught you there also. This is a very important concept and very interesting concept also. It says that it is not possible to measure both the position and momentum of particle at the same time exactly. For us, what is particle now? We are talking about electrons. For us, electrons are the particles now. So this Heisenberg's uncertainty principle, it actually stated that we cannot know both the position and momentum for a particle at a time. That means in an orbital, we can never know exactly where an electron is at that particular instant of time. So we cannot draw the orbitals occupied by the electron exactly. Okay, that's why we are using this word most probable. We are using this mod psi square, no? That is the reason why, because we cannot exactly say where is the electron in that orbital at that particular time. This is happening because of Heisenberg's uncertainty principle. See, this is based purely on quantum phenomena. So, by this time you should have understood that molecular orbital theory is based on quantum phenomena. So, Heisenberg's uncertainty principle, here for example, we have taken the position and the momentum. It says that if I multiply both of them, the value I am going to get is h by 4 pi always. Either this x into p will either be greater than h by 4 pi or it will be equal to h by 4 pi. Okay. In this figure only you can see how fast the electron is moving. Can you catch the electron particularly at that time? It is not possible, right? When you cannot catch it, how can you find the exact position at particular time? It's not possible. Okay. So this molecular orbital theory is based on this concept. Actually, this chemical bonding, no, it was explained by two theories. First theory which explained the chemical bonding is valence bond theory, VBT. But what happened was it had few drawbacks. Because of these drawbacks, no, this theory did not work well. But for a certain extent, it explained many things in chemical bonding. But because of few drawbacks, some other theory came into picture which worked well, and that theory is the molecular orbital theory. As I told you earlier also, this molecular orbital theory, it gave the quantum mechanical treatment of bonding by describing electronic structure of molecules. It took molecules into picture. It did not just stick to atoms. Okay. So let's talk little bit about valence bond theory. Then we will move on to our syllabus of molecular orbital theory. Actually, valence bond theory is also there in your syllabus. It is there in this chapter named chemical bonding. I will talk in that chapter. I will talk more clearly on valence bond theory. But here we need to know little things about valence bond theory to understand molecular orbital theory. At least we should know why molecular orbital theory came into picture, right? What was the need of that molecular orbital theory? Molecular orbital theory means from now onwards, maybe I will call it as M.O.T. You have to understand that I am talking about molecular orbital theory. Okay. Now, valence bond theory or VBT, actually it described chemical bonding. It says that chemical bonds are formed when atomic orbitals overlap. What did it say? It says that the chemical bonds are formed when atomic orbitals overlap. Or in other words, it stated that overlap of incompletely filled atomic orbitals will lead to formation of a chemical bond between atoms. Means if there is a incompletely filled atomic orbitals, then if those type of orbitals will overlap, then there is a formation of chemical bond. This is what valence bond theory told. This was a very acceptable theory because see, if there are incomplete filled atomic orbitals, then chemical bonds can surely form, right? There is a space for electrons to stick together. But then after explaining this also, there were few drawbacks of valence bond theory. What were they? Means, first of all, it could not explain few facts. Few facts like why carbon is tetravalent. It didn't tell. Carbon is tetravalent, right? But why it is? What is the phenomenon behind this type of bonding? Valence band theory, it could not explain. Then it could not predict a bond angle. There are certain angles between the bonds formed, right? It could not predict why this is happening or what is the procedure to calculate those bond angles. All that it did not say. Then one more very important drawback of valence bond theory is that it assumed that electrons are localized. We all know today very nicely that electrons are not localized, right? They are revolving around the nucleus. But because of this assumption, valence bond theory, I can say that it failed at this point. Because it assumed that electrons are localized in certain areas, which is not right. That we also know. Basically, valence bond theory, it sticked to an atom. It told that by combining atomic orbitals on the same atom, hybridized atomic orbitals can be formed. Okay. It talked about hybridization, which is right. What is hybridization? Hybridization means mixing of atomic orbitals to form new atomic orbital. And this was happening because of overlap of incompletely filled atomic orbitals. Okay, this was okay. This concept was very nice with the valence bond theory. But because of these concepts, it sort of failed. Now molecular orbital theory came into picture. As I told you earlier also, molecular orbital theory, it gave quantum mechanical treatment of bonding by describing the electronic configuration of molecules. Before molecular orbital theory, one knew about electronic configuration of an atom. We knew it, right? 1s2, 2s2, 3s1. We write the electronic configuration of atoms, right? This was known. But molecular orbital theory, it gave electronic configuration for molecules. That is one speciality of molecular orbital theory. This M.O.T. it was given by Hund and Mulliken, and it was based on linear combination of atomic orbitals model. Here also there was combination of atomic orbitals like in valence bond theory, but here molecules were considered. So what all it said? First of all, what is said is Like atoms have atomic orbitals. Actually, how are atoms formed? Actually, atoms are formed by overlapping of atomic orbitals, right? In the same manner, molecular orbitals overlap and form molecules. This M.O.T. told. In the same manner, M.O.T. told that molecules can be formed by overlapping of molecular orbitals. See, for atomic orbitals, how we wrote electronic configuration? We wrote it like this, right? 1s1, 2s1, then 2p, then 3s, and so on, right? Then for p we had 3 orbitals, px, py, and pz. So this is how we used to write, right? So what we had names for these atomic orbitals? S, p, d, f, isn't it? For p we had 3 orbitals, that px, py, and pz. Then for d we had 5 orbitals. We have that no dx, dy, dz, then dxy minus yz, and all that is there. Anyway, we don't need it right now. In the same way, for f we had 7 orbitals, isn't it? Similarly, molecular orbitals were given different names. What were the names given? They were like sigma, pi, delta, and all that. So this is sigma bonding. Symbol is the Greek letter sigma. Sigma bonding. The pi bonding. Delta we don't need right now anyway. So pi bonding. So these are the type of bondings given to the molecular orbital bonding. Now what is sigma bonding and pi bonding? See, actually valence bond theory also was talking about the covalent bonds only. Molecular orbital theory is also talking about the covalent bonds only. But there are differences, okay? For example, this sigma and pi bonding, they are covalent bonding only, but they differ in overlapping of atomic orbitals. See, I will give you one funda here to remember. Sigma means it will be head-to-head overlapping. That overlapping only will look you like this. Overlapping of orbitals only will look you like sigma. Here, head-to-head overlapping of atomic orbitals will happen. Pi means the overlapping only will look like pi for you. Okay, there will be lateral overlapping of 2 atomic orbitals. Side overlapping. Actually, both overlappings will be in same phase, but the type of overlapping will be different. Okay, in sigma, there will be head-to-head overlapping of atomic orbitals. In pi bonding, there will be lateral overlapping of atomic orbitals. Okay. So next to this molecular orbital theory, it also told that how many number of molecular orbitals are formed, how you will know means those number of molecular orbitals formed, it will be equal to number of atomic orbitals formed together. See, for example, if you have this 2 orbitals are there. Okay, say for example, this is a 1s orbital and 1s orbital. Okay, if one atomic orbital is formed by these 2 orbitals combining together, then molecular orbital will also be formed in the same manner. Means there are 2 atomic orbitals, means number of atomic orbitals here are 2, no? So number of molecular orbitals will also be 2 here. That is what molecular orbital theory told. Okay, so we don't need to worry much that what is happening in molecules and all that. Whatever is happening in atomic orbitals, same thing is happening in molecular orbitals. Now, we are treating this electron, I mean the molecular orbital theory is treating this electron as a wave, right? So, what will happen if 2 waves, they will interact with each other? There is something we call as interference, right? What is interference? Interference means it is a superposition of waves. See, for example, I have one wave. I write it like this. Let the wave function for this wave be psi 1. Then again, I am superimposing another wave with wave function psi 2. both waves are in same phase. You can see both waves are in same phase. Now if this superposition happens between those two waves, what will be the result? The result will be a bigger wave with more amplitude, because same phase is there, right? So here interference is happening, superposition of two waves is happening, and I am getting a bigger wave. This type of interference is known as constructive interference. Now there could be another situation also, right? If I have a wave with wave function psi1, and if there is a overlapping of this wave with another wave with wave function psi2, and I am not getting any wave. There is no addition of waves here, there is subtraction of waves. This will lead to a zero wave. The wave vanishes when these two waves overlap. This type of interference is known as destructive interference. Now, instead of these waves, if I keep orbitals, see if I have a 1s orbital overlapping with another 1s orbital. Now I have two situations, right? What are the two situations? One situation could be of constructive interference, the another situation could be of destructive interference, isn't it? Let this be psi1 and let this be psi2. If I have a constructive interference, then I will have psi1 plus psi2. Okay. If I have a destructive interference, then I will have psi1 minus psi2. Whenever I have this constructive interference psi1 plus psi2, the molecular bonding is happening. If I have destructive interference, then the bonding is known as anti-bonding. We denote this anti-bonding by star. Okay, bonding and anti-bonding. Remember, constructive interference is giving us bonding. Destructive interference is giving us anti-bonding. This you have to remember. Now we are talking about bonding and anti-bonding, right? Bonding of molecular orbital will be stable. Why it will be stable? Because it will have less energy, isn't it? The molecular bonding will have less energy because the molecular orbital is stable. It does not need to distract itself. That's why it will have less energy. Anti-bonding molecular orbital, it will be jumping, isn't it? It will be unstable. It is unstable means obviously it will have more energy. See, in your HSTR and KREIS, they can ask any of these type of questions. They will make one MCQ and they will ask. You should know these points. That's why I'm telling you like a story. And also this is a very important topic, not only for your HSTR and KREIS and other competitive exams. As a science teacher, especially a chemistry teacher, you should know molecular orbital theory because it is very different and very interesting, right? Okay. So here in this figures, I am showing you how this superposition happens. See, if this is a constructive interference, what is happening? The amplitude will increase. If there is amplitude is A is there means in the product wave, I will get the amplitude as 2A. A plus A. If this amplitude of this wave is A, amplitude of this wave is A. If both waves are in phase, then superposition happens. Then I will get a wave with amplitude 2A. Okay. And then we were talking about these nodes also, right? See, here I am showing you as a wave function here. Here I will have one node. Here there is less probability of finding the electron. Okay. For constructive interference, there is more probability of finding the electron. It comes inside. And one more important feature of molecular orbital theory was that the combining of molecular orbitals, it must have same or nearly same energy. This is very important point. Same or nearly same energy. If those orbitals will have, then only they can combine together. Not only energy, their shapes also should be same. For example, 1s will try to combine with 1s only, or px orbital will try to combine with px only. 1s it will never try to combine with px. Okay, Px it will never try to combine with Py also. It wants Px only, then only they can combine. If there is Py orbital, then it will combine with Py only. Okay. So these are the salient features of molecular orbital theory. Now let me give you a quick summary with what all story I have told you till now. First of all, atomic orbitals, they will undergo LCAO or linear combination of atomic orbitals to form same number of molecular orbitals. Okay, this will happen if they fulfill these 3 or 4 conditions. What is the first condition? The atomic orbitals, they must have same energies, comparable or nearly same energies. Then atomic orbitals, they must overlap linearly for enough and effective overlapping. Linearly means sigma bonding should happen. Then atomic orbitals, they must have same symmetry along with major molecular axis. For example, if we are talking about z axis, means then pz orbitals will only overlap. Px and Py will not overlap. Okay, so I told you all this, right? Then molecular orbitals, they are formed due to constructive and destructive interference of atomic orbitals. Then this constructive interaction of orbitals, this will happen between the orbital lobes with the same wave function psi, and this will produce bonding molecular orbitals. What are the bonding molecular orbitals we were talking in molecular orbital theory? That is sigma bond, pi bond, delta bond, all these. Okay, these are known as highest occupied molecular orbitals. Okay, we will talk about the sigma and pi bonding now. How is this formation of various molecular orbital possible? That we will see here. First, let's talk about sigma bonding. I told you that sigma bonding, it will look like sigma only, right? It is just a funda for you all to remember. Sigma bonding means this is a axial atomic orbital interference, you can say. Axial atomic orbital interference. We are talking about interference only right now. That's the reason why molecular orbitals are formed. See, for example, if I have two 1s electrons, this is one electron, the other one is other electron, and I am having one constructive interference between them. So there is a constructive interference. Then what will be the orbitals formed? They will be in this shape. Plus and plus will be there. There will be bonding between them. You can see this is looking like sigma, right? Okay. So this is your bonding molecular orbital. Now what will happen if there will be a destructive interference? This is 1s orbital. Then the other one is also there. I have a destructive interference now. What will happen if I have a destructive interference? I will have something like this. These lobes will be formed like this, and I will have this nodal plane. We were talking about node, right? I will have a node here. Node means no electron density. There are 0 chances of finding an electron. In fact, there will be no electron in this place. So they can ask you a question. In sigma bonding, if 1s and 1s orbitals are combining together, how many nodes you will find? You will find one node here. Okay. Now, this was bonding molecular orbital, right? The another will be anti-bonding molecular orbital. You write it as sigma star. Okay. This is what we called as sigma bonding. In the same manner, you can do for 2s and 2s also. Now, this story only I can write it in another way. I will write it like this. Either 1s or 2s. In place of writing this arrow marks in this manner, I will just write it like this. I'll write it like this, and then another thing, and then these are the two situations. Okay, what will happen if addition is happening? What will happen if subtraction is happening? Here I have showed you the entire picture very clearly. This is the bonding and this is anti-bonding. Okay, so they can ask you any question based on any of these stories. You should know. That's the reason why I am writing and explaining you this class, especially because we need to talk on this topic in this manner only. Wherever writing is needed, I write. Wherever writing is not needed, I don't write, because writing takes little time, right? I don't want to waste time. But here, you are spending time watching this class means it is worth for you, because no one will explain you molecular orbital theory so slowly in detail the way I am explaining. Okay. Now this was about oneness and oneness, right? If I want to talk about PZ, how it will be? It will be like this. How you do? You take two PZ orbitals. This is one PZ orbital. The another one is this PZ orbital. Overlapping is happening. I'll write it here for you. Plus, minus, again plus, minus. Then constructive interference is happening. If constructive interference is happening, what will happen? It will become like this. The bonding will become like this. Here I will have two nodes. This one will be minus, this one will be minus, and this one will be plus. I will have one node here, another node will be here. So total nodes, if PZ orbitals are overlapping, there will be two nodes. Okay, this was your constructive interference. Then what will be your destructive interference? Actually, I should have written like this. Okay, then destructive interference, how it will be there? It will be like this. Again, there will be little gap, and again it will be like this. You will have one node here, another node here, and another node here. There is no electron density, right? So you will have three nodes here with minus plus, again minus plus. You will have three nodes here. This will be your anti-bonding. Sigma star 2pz you write. Here this one will be bonding. You write just sigma 2pz. Okay. So this is bonding and this one will be anti-bonding. In anti-bonding you have three nodes. In bonding you have two nodes. Okay. And this was your destructive interference. Now this was all about your sigma bonding. Remember, it looks like sigma, right? It looks like sigma. After bonding also it looks like sigma. Now let's talk about pi bonding. Pi bonding means I told you that it is a sidewise. Okay, it is a sidewise atomic orbital interface. Sidewise you can say. For this, let's take example of Py. Py will be like this, right? It will be in y direction, plus, minus. Now there is overlapping of this again, plus, minus. Then you will have one constructive interference, another will be your destructive interference. Like this we write, right? Like this we write. Then for constructive interference, one thing will happen. Again for destructive interference, one thing will happen. For constructive interference, this lobe will go like this, up and down. You will have one node. This is node, right? This is your bonding. For destructive interference, this lobes, no, it will become like this. Means you have one node here, another node here will be there. So you have two nodes here. For pi star, it is anti-bonding, right? Pi star 2py, you will have anti-bonding, two nodes will be there. I have picture also, I will explain you like this also. See, either 2px or 2py, they are overlapping, addition and subtraction is happening. You will have one nodal plane here and here you will have two nodal planes. In the picture you can see clear figures actually. I have not drawn so clearly. Okay, so these are the formation of various molecular orbitals in molecular orbital theory. I hope that you have understood sigma and pi bonding very nicely now. See, the funda I told you for sigma is valid for pi also. See here, this looks like pi, right? This looks like pi. Even after bonding, it looks like pi. This is how you can remember. Okay, this is pi bonding. Now, molecular orbital theory was also successful because, like atomic orbitals, molecular orbitals also, they follow all these principles. For example, Pauli exclusion principle is there. What does it state? It states that any molecular orbital can have a maximum of 2 electrons with opposite spin, right? So, this is valid for molecular orbitals also. Next is Hund's rule. In degenerate molecular orbitals, before pairing, each molecular orbital, it will have one electron. Then only next electron will come. This is valid for atomic orbitals also and for molecular orbitals also. And the third one, the Aufbau principle, the way we wrote the electronic configuration, that is also valid for molecular orbitals. Electrons, they will be filled from one molecular orbital of lower energy. Then we will go to higher energy. Now another important concept we have to talk based on molecular orbital theory is the bond order. We have one formula for this bond order. This bond order is equal to Nb minus Na upon 2. Nb will be number of bonding molecular orbital electrons and Na will be number of anti-bonding molecular orbital electrons. So if you can find the number of bonding orbital electrons and number of anti-bonding orbital electrons, then you can easily find the bond order. Okay, this is one procedure. Other thing is that this bond order, no, this is directly proportional to two things: bond dissociation energy and bond angle, and it is inversely proportional to bond length. See, any of these points can be asked as MCQs. That's the reason why I am mentioning this. Okay, remember bond order, it is inversely proportional to bond length. So higher the bond order, higher will be the stability. Okay, and shorter will be the bond length, because bond order is inversely proportional to bond length. And one more thing is that if you have unpaired electrons, for example, if you are in the principal quantum number, it will be 1, 2 or something like that. If the unpaired electrons are present in a molecule, then that molecule will be paramagnetic. This is the speciality of molecular orbital theory. It will give you the magnetic nature of orbitals. Okay, if you have unpaired electrons, then that molecule will become paramagnetic. And if you have no unpaired electrons, then that molecule will become diamagnetic. They can ask you as MCQ, that's why I am mentioning here. If you have paired electrons, then the molecule will become paramagnetic. If you have unpaired electrons, then the molecule will become diamagnetic. Okay. Now, based on that bond order only, we have taken one example of oxygen. The oxygen O2 is there, but it is having a different charge. This oxygen ion, it has different charge. Okay, it is minus 2, plus or plus 2. See the way the bond order, it is decreasing here. The bond order is decreasing from 3 to 1. Okay, you have to remember, if the charge is decreasing, then the bond order is decreasing. Decreasing order of bond order means the bond angle and bond dissociation energy will also decrease. Only bond length will increase. And then how it will show the magnetic nature? I told you it shows the magnetic nature, right? If you have N is equal to 2, then it is paramagnet. If N is equal to 0, then that molecule will be diamagnet. And if it is in between, if N is equal to 1, then that molecule will be paramagnet. Okay, actually there are so many things to learn in molecular orbital theory, but I don't think that you need to go into so much deep. They will not ask you so many tough questions. They will only ask you the general questions based on this topic. Okay, that's why I am giving you just the gist. I am not going into much deeper. Now let's see what type of questions may be asked. First question is, stability increases as the energy. See, they are talking about a molecule. The molecular stability, it increases as the energy increases, doesn't change, decreases, increases, and then decreases. It should be decreases, because if the stability increases, the energy of that substance will decrease. The higher the energy, the less stable the molecule is. We were talking this in this constructive and destructive interference, right? The bonding and anti-bonding. So stability, it will be inversely proportional to the energy. Not only in molecular orbital theory, this is true for entire of the universe. Next question. Which of the bonding orbital has greater energy comparatively? If you see all the four options, the bonding orbital energy, it will be greater for anti-bonding. We told, right, for bonding the energy is less, for anti-bonding the energy will be more. Next question. What's the bond order of oxygen? Oxygen, simple thing, right? If you draw the Levy diagram, then you will know that then the bond order is 2 for this. The next question is, the filling of molecular orbital takes place according to, see, even if you have to fill the molecular orbital, you have to follow all these principles, right? Hofbauer principle, Pauli exclusion principle, Hund's principle. So all of the mentioned will be the right answer. So 2 electrons in the same orbital, they cannot have the same set of all 4 quantum numbers identical. That's why we have to follow all these principles in order to fill the molecular orbital. Next question. According to molecular orbital theory, the shape and size of a molecular orbital depends upon. Actually, the shape and size of the molecular orbital, it depends upon shape, size, number, and orientation of combining atomic orbitals. So all of the mentioned options are right here. So option D will be the right answer. Next question. The oxygen molecule is paramagnetic. It can be explained by, of course, paramagnetic, diamagnetic or weakly paramagnetic. All these things are explained by molecular orbital theory. Next question. Anti-bonding molecular orbitals are produced by anti-bonding molecular orbitals. When they are produced when destructive interaction of atomic orbitals is happening, isn't it? Constructive will give you the bonding molecular orbitals, destructive will give you the anti-bonding molecular orbitals. Now I have a question for you. You all should answer this question in the comment section. You just write the option A, B, C or D. The question is, pi bonds are formed by which of the following orbitals? So based on my explanation only, you have to answer this. After watching the entire video, I am sure that you can answer this question. Okay, please let me know the answer in the comment section. I'll be glad to know your answers. Okay then, that's all for this lecture. We complete the molecular orbital theory part in this lecture. And also please do like, share and subscribe to my channel. And also please keep in touch with the subjects, keep watching my videos and also keep reading, because HSTR and KREIS notification, it will be anytime, it will be coming soon itself. Okay, that's why you have to be ready. Okay friends, thank you, all the best, bye.